Previously, I have argued that determining the causes of mass extinction or other events in deep time relies on having good chronologies and correlating events with precision. Then we must consider sampling and mixing artifacts. These do not tell us much about history and causes, but instead spread a veil over the causal processes. In addition, we'll be on safer ground in our explanations if we collect many different types of relevant data for comparison. In the case of mass extinctions, we need good dates, good timescales, correlation, stratigraphic ranges of multiple fossil groups, and as much environmental data as we can muster. We know that each type of data comes with its own problems, but the assumption is that if you have broad agreement between multiple types of data, you're probably on the right track. For instance, in my own work on the climate of the Cretaceous greenhouse, we used temperature estimates from oxygen isotopes, magnesium-calcium ratios, and an organic biomarker method called TEX86. The results of each method helped to reinforce the conclusions of the others, helping us make the case that the greenhouse was unusually hot, with ocean temperatures over 35 degrees centigrade compared to the high-end temperature in the modern ocean of around 29 degrees centigrade. Ideally, we'd also try to model this system so that we can understand the mechanistic explanation better than would be possible by just comparing observational data. Now, in our models of the Cretaceous greenhouse, for instance, it turned out that we needed really high concentrations of greenhouse gases to make the model replicate our observed temperature estimates. This result could mean that our temperature data were bad after all, despite having lots of them, or that there was really high concentrations of greenhouse gases, like the model suggests, or still another possibility was that something was missing in the model. In the case of mass extinctions, we are clearly getting to fairly good understanding of some of them. When I started my career, we still wondered why there were so few places in the world that preserved the actual stratigraphic boundary between the Cretaceous and the Paleogene. It turned out that we just not looked very hard. Now we have found hundreds of sites around the world where the boundary event is preserved. We have drilled into the crater and mapped the distribution of ejecta globally. We have likewise intensively sampled and dated the Deccan traps. We have sampled and resampled fossil assemblages to work out what is mixing and sampling artifacts and what is reality. And we are increasingly modeling the system with better and more realistic models. Consequently, the science is well beyond hand-waving speculation. We are now much into refined views of the nature of the Cretaceous ecosystems before the extinction, the impact of volcanic events themselves, and understanding the aftermath, including how the extinction shaped the subsequent diversification of life. Now, understanding of the great PT extinction is probably a decade or more behind that of the Cretaceous-Paleogene event. PT boundary sites are still rare, and our understanding of the mechanistics of volcanism that could drive a huge extinction is pretty speculative. But at least now we are paying attention, and the discoveries are coming fast. Both the KPG and PT extinctions appear to be bolt-from-the-blue events with strong solitary causes. This raises the philosophical problem that modern science often makes an implicit assumption that there are single causes for most historical phenomena. Indeed, the culture of science strongly favors finding examples of direct determinism, where there's just one strong cause. And the pages of top journals like Science and Nature are full of these sorts of examples. Naturally, we like these cases because each phenomenon is linked fairly directly with a single known cause. The KPG boundary is a case somewhat like this. We have identified the ultimate cause, namely an impact, that has the power to do what we attribute to it. That we don't know all the details is okay for the most part, because we assume a fairly simple connection to the ultimate cause. The impact itself is so powerful and globe-spanning that it is easy to assume that it had the power to create a global mass extinction, even if the details are messy and the causes of extinctions of foraminifera may not be quite the same as those for dinosaurs. But we should also consider that some patterns could result from stochastic variables, that is randomness, and do not require a unique causal explanation, at least not a single one. An example is what I call the Joshua Epstein process, named for a researcher at the Santa Fe Institute in New Mexico. Epstein investigated why people tend to sort into relatively homogeneous neighborhoods, according to race, income, ethnicity, or other factors. He created computer models in which initially well-mixed populations were found to sort out into very homogeneous patches as a function of very slight favoritism for aspects of one's life associated with particular ethnic groups. His computer model took into account people's preference for being in communities with broadly similar wealth, social conventions, whether houses have pools or not, public infrastructure like parks, racial groups, etc. The result was clear differentiation of people by race, but this was because of a myriad of small choices rather than outright racism per se. What I find particularly fascinating is what happened next. Epstein was messing with computer models so he could run the same experiment over and over again to see if there were common patterns. But it turns out that when he mixed the populations again and reran the model, people did indeed become separated into groups as before, but they were in different physical places than the original model, and not all of them were strongly correlated with race. The model always produced clusters, but where the clusters are and who is in them is indeterminate. The lesson is that simple rules can result in complex behavior, but do not necessarily produce the same exact result when the experiment is run over and over again. This is the problem of contingency. That is, history is the product of a chain of events, not a single overwhelming strong cause. The chain of events can be torqued into a new outcome through very small changes along the way. These considerations suggest that we can get a pattern that looks like it requires a strong causal origin, while in fact many patterns are made by lots of weak causes, rather than any single strong ones. The lesson is that not all patterns, including ones that look really deterministic, really reflect single powerful causes. To be sure, we really don't like the messy multi-causal systems very much, or those that result from weak determinism, and papers describing such examples are actually probably pretty hard to publish. The question remains then whether nature really is dominated by lots of causes of direct determinism. Or do we just happen to see nature that way because we're hunting for examples that are simple to understand?